IGCSE Physics student, are you ready for your IGCSE Physics paper for May June 2025, paper 43? In this video, I am going to walk you through the entire paper step by step so you will know exactly how to answer with confidence. So what are you waiting? Grab your pen, grab your past year paper, let us master this paper together. Now, let us begin with the first question. Number one, a car travels at a speed of 20 meters per second. The driver applies the brakes when he sees a red traffic light. Fig 1.1 shows the speed time graph for the car. This is a speed time graph. A, determine the speed of the car at time equals to 2 seconds. Now you look at your x-axis because the time is at the x-axis. Look at the x-axis. Where's my 2 second? 2 second is here. So 2 seconds and go to your y-axis. What is the value on the y-axis? Is the middle between the boxes here. Okay, so I get the value here. This is 10, this is 11, this is about 11.5. So I'm going to put it as 11.5 meter per second. Now, B, calculate the distance traveled by the car between time equals to 0 and time equal to 4 seconds. Remember, this is a speed time graph. Speed time graph. So whenever you're asked to calculate the distance from 0 to 4 seconds, it is basically asking you to calculate the area under the whole graph here. This is the area of trapezium. Right, I'm going to use the area of trapezium. Do you recall the area of trapezium? So I'm going to write first, distance travel equals area under graph. And the area is the area of trapezium, half A plus B. What is the A value? So this is my A value right here. Okay, this is 0.1, 0.2, 0.3, 0.4, and this is 0.5. And B value is 4. So it is 0.5 plus 4 times the height, which is 20. So I'm going to times 20, use your calculator, and the answer that you should get is equals to 45 meter. 45 meter is the answer. Now C, calculate the deceleration of the car between time equals to 0.5 second and time equals to 4 second. Now this is a speed time graph. How do we calculate deceleration? Right? Deceleration is actually equals to the gradient of the graph. Gradient of graph. So for you to find the gradient, you need to have two coordinates because the formula of gradient is y2 minus y1 over x2 minus x1. So I get my value of x2, x1 and y1 because it is from time t equals to 0.5 second, remember, and to t equals to 4 second. So I get the value here, 0.5 is my time. My speed is 20, and at 4, time is 4, but the speed is equal to 0. Now, okay, y2, you need to get a negative value because this is deceleration. y2, I put it as 20 minus 0. x2, I put it as 0.5 minus 4. It doesn't matter which one you want to put it as x2 and y2. I put this as x1 and y1. This is x2 and y2. You can put it in the other way around, it doesn't matter. So you would end up the same answer as mine. So I got negative 5.71 meter per second square. So negative 5.71 meter per second square is the answer. Right? So that's all. Now, question number 2. Fig 2.1 shows a space vehicle which consists of a capsule and a nose cone. The space vehicle is moving at a velocity of 7,800 meters per second. The mass of the space vehicle is 840 kilograms. A, show the momentum of the space vehicle is approximately 6.55 times 10 to the power 6 kilogram meter per second. Now, do you still recall the formula of momentum? Momentum is being defined as mass multiplies by velocity. The mass of the space vehicle is given, which is 840. Could you see that? And the velocity is 7,800. Use your calculator. The answer that I got was 6.552 times 10 to the power of 6 kilogram meter per second. Now, showing the intermediate answer before you round it off to the answer that I asked you to show is super important. So you have to show this before you round it off to 6.55 times 10 to the power of 6 kilogram meter per second. B, the capsule ejects the nose cone, as shown in Fig 2.2. Determine the velocity v of the capsule after the nose cone is ejected. Give your answer to 3 significant figures. This is super duper important. 3 significant figures. I am definitely going to use the principle of conservation of momentum. If you remember, states that the total initial momentum equals to the total final momentum of the whole system. The total initial momentum is just the momentum of the space vehicle, which is 6.55. Okay, I'm going to write it down because I have already calculated it. Is equal to the final momentum. Final momentum is the momentum of the capsule and the nose cone. Right, so the capsule, the nose cone first, which is 720 times a V, because the nose cone and the capsule, right, are moving in the same direction. So I put positive to both velocity, plus so 120 times 7,850. So make V as the subject. V is equal to 6.55 times 10 to the power of 6 minus 120 times 7,850 divided by 720. Therefore, your answer should be 1, 2, 3. 7.79 times 10 to the power of 3 meter per second. 1, 2, 3, 7.79. That's the answer I got, but try to confirm it again. 6.55 times 10 to the power 6 minus 120 times 7,850 divided by 720, and I round it off to 1, 2, 3. Yes, 7.79 times 10 to the power of 3 meter per second. 3 significant figures, remember? Times 10 to the power of 3 meter per second. That's the answer. Question part C. A different space capsule returns to Earth. Fig 2.3 shows the capsule just before it lands in the sea. The capsule travels at terminal velocity. Do you still remember what is terminal velocity? Terminal velocity means a constant maximum velocity when the resultant force acting on the capsule is equal to 0. The upward vertical force acting on the capsule is 120 kilonewton. Calculate the mass of the capsule. Remember, I did explain terminal velocity. I said the upward force is balanced by the downward force. Since the upward force is being given as 120 kilonewton, the weight of the capsule must be 120 kilonewton as well, because the resultant force acting on the capsule is equal to 0. So to find the mass, I need the weight. Weight is equal to mg. Weight of the capsule is 120 times 10 to the power 3, that's kilo. Mass times the gravitational acceleration, which is 9.8. Right, now the mass would be equal to 120 times 10 to the power 3 divided by 9.8. And the answer is 1.22 times 10 to the power of 4 kilogram. Now 1.22 times 10 to the power of 4 kilogram. Now, let me write you some notes here to remind you when you do revision, right? Terminal velocity, okay, meaning to say that the resultant force acting on the capsule, must be equal to 0. That also means that the upward force on the capsule is equal to the downward force. on the capsule. In this case, the downward force of the capsule is equal to weight, if you want to know further. Now, weight is equal to mg. So that's all. Now, let us continue with question number 3. Fig 3.1 shows an archer aiming an arrow at a target. The archer pulls back the bowstring, doing a total of 110 joules of work. Her hand moves a distance of 0.45 meter. The bow is bent and stores energy. Show that the average force applied by the archer in pulling the string back is approximately 240 Newton. Since the work is being given, I'm going to use the definition of work to solve this. Work is equal to force multiplied by the distance moved in the direction of force. Work is given, which is 110. Force, I don't know, but the distance moved in the direction of force is 0.45 meter. Therefore, force is equal to 110 divided by 0.45. And the value that I got was 244.44 Newton. And I round it off to 240 Newton. B, the archer releases the bowstring. All the energy in A is transferred to the arrow. The arrow moves off at an initial speed V. The mass of the arrow is 0.03 kilogram. Calculate the initial speed V of the arrow. In this case, I would like to use the principle of conservation of energy because the work done, right, the work done is transferred to the arrow because the arrow is moving. So that is why the work done is transferred to the kinetic energy of the arrow. So the work done is given as 110 joules. The kinetic energy of the arrow must be half mass of the arrow times the speed of the arrow. You square it. So 110 is equal to 1 half. Mass of the arrow is 0.03 v squared. Now you make speed as the subject, which is 110 times 2 divided by 0.03, and you square it the whole thing. The speed of the arrow is 86 meter per second. 86 meter per second. Now explain why the speed of the arrow as it hits the target is less than the value in B1. Remember, we are surrounded by air particles. So some of the initial work must be used to overcome the air resistance experiences by the arrow. So I will say some of the initial work is used to overcome air resistance acting on the arrow, because as long as object is moving, there will be air resistance acting on the object. Air resistance is the hindrance by air particles acting on the moving object. Question number 4, Fig 4.1 shows the pan with a copper base on a hot plate. The hot plate hits the pan and the water. Explain how thermal energy is conducted through the copper base. Now you have to understand one thing is that copper is a conductor. Conductor contains delocalized electrons. It is not just by vibrating the particles in the copper base, but also delocalized electrons inside the copper base will help to transfer the thermal energy. So I'm going to make this, okay, explanation right now. Okay, particles, I would write particles in copper base absorb thermal energy from hot plate. And when they absorb energy, don't you think they gain energy? So they gain energy, these particles vibrate and collide with neighboring particles to transfer and neighboring particles first. Okay, heat is being transferred. Heat is being transferred to neighboring particles. And this process continues until the whole copper base is heated. Okay, and at the same time, right, delocalize, I'm sorry, spelling problem here, delocalize. Electrons absorb heat and gain kinetic energy and collide with themselves and vibrating particles in copper to transfer the heat to the whole base of the copper. So that's the answer. Now B part 1, define in words specific heat capacity. So specific heat capacity, if you don't remember how to define it, I will always write down the formula first. E equals to mc, change in temperature. C is the specific heat capacity, is the energy, right? Divided by mass times the change in temperature. So it is being defined as the heat or thermal energy supplied per unit mass to increase the temperature of the substance, right? Right. To cause a change in the temperature of the substance is also okay. Now, the second part, a student heats the metal object to 100 degrees Celsius. The student places the metal object in an insulated cup containing water at 22 degrees Celsius. The final temperature of the water in the metal object is 31 degrees Celsius. Specific heat capacity of the water is given as 4.2 joules per gram per degree Celsius, and the mass of the water in the insulated cup is 50 gram. The mass of the metal object is 54 gram. Calculate the specific heat capacity of the metal. Could you look at the mark given? It is 3 marks. So how do you do that? If you face difficulties, I would strongly suggest you to draw a diagram so that you can see clearer. I have a metal object. I have been heated out to 100 degrees Celsius. And then I place this heated object into a cup, insulated cup, which contain water. And initial temperature of the water is 22 degrees Celsius. So when you place a hot object into the water, you definitely know that heat is going to transfer from the hotter metal object to the water to increase the temperature of the water. Don't you think so? And then eventually the final temperature of both objects will be the same at 31 degrees Celsius. Now, to solve this question, the easier way to solve it is by using the principle of conservation of energy, which I'm going to use it right now. So I would say that the heat, right, lost by the metal, because the metal is a higher temperature, heat lost by metal object is being gained by, okay, heat absorbed by water. Now, heat loss by the metal object. So I put mass of the metal. MM means metal. Specific heat capacity of the metal. The change in the temperature of the metal object is equal to heat loss absorbed by the water. Mass of the water, specific heat capacity of the water, and the change in temperature of the water. Mass of the metal is being given, which is 54 grams. So I'm going to change that gram to kilogram divided by 1,000. Specific heat capacity of the metal is the one that I need to calculate. The change in the temperature of the metal is 100 degrees Celsius. You take the larger temperature minus the smaller temperature. So minus 31 degrees Celsius, because I have already mentioned this is a heat loss by the metal. So it's equal to mass of the water is given as 50 gram. So I'm going to change to kilogram as well. Specific heat, oh, I'm not going to change to kilogram because specific heat capacity is given in joule per gram. So don't change to kilogram, just put it as 54, just put it as 50. So remember that you have to look at the unit of specific heat capacity. So I'm not going to change that. I'm just going to put it as 54 gram, 54 grams, sorry. And then for the mass of the water, this is 50 gram. Specific heat capacity is 4.2 per gram, remember. And the change in the temperature of the water is from, okay, take the larger temperature, 31 degrees Celsius minus 22 degrees Celsius. Now you have to make your specific heat capacity of the metal as the subject, but I am going to do this first, intermediate, yeah, times the specific heat capacity of the metal times 69, change in temperature is 69, and this is 50 multiplies by 4.2 multiplies by 9. And then the specific heat capacity of the metal is equal to 50 times 4.2 times 9 divided by 54 times 69. And the answer that I got was 0.507 joules per gram per degree Celsius. So joules, 0.507 joules per gram per degree Celsius. Now, question number 5. Fig 5.1 shows 4 rays of red light, P, Q, R, and S, coming from a spotlight in a swimming pool. A, define in words refractive index for a ray of light traveling from air to water. So traveling from air to water, refractive index is being defined as the ratio of speed of light in air to the speed of light in water. Done. B, Fig 5.1. On Fig 5.1, draw the path of rays P and Q at the water-air boundary. Could you see that P is traveling, okay, straight, right, towards the surface of the water? So P is acting, the ray of P is acting at the line of normal. So you continue the ray will just be a straight line. Whereas for Q, you need to draw a normal. What is normal line again? Normal is just an imaginary line, right? That is acting perpendicular to the water surface. So since the ray travel from denser medium, which is water, to the less dense medium, the ray would be refracted away from normal. So as long as you draw refracted away from normal. So that's the answer. So you can see this is a path of P, this is a path of Q. Now, see the angle of incidence of ray R is 49 degrees. Calculate the refractive index of the water. Let us look at R. R travel from the water to air. It causes the ray of R to be refracted at 90 degrees or at the surface, interface of the water and air. So R is definitely your critical angle. So N is equal to 1 over psi critical angle, which is easier. Now 1 over psi 49 degrees. So you should get 1.33. 1.33 is the answer. D, explain why ray S is totally internally reflected at the water surface. First of all, condition for the total internal reflection is that the light ray must be traveling from the denser medium to the less dense medium, which is true in this case. And secondly, the angle of incident, right, of ray S, which is larger than the critical angle of the water. Right, so that is why the light is internally reflected into the water. So I'm going to say angle of incident. Okay, first of all, light or ray as. Okay, just write down ray as will do. Ray as travels from denser medium, which is the water, to less dense medium, which is the air. Okay, and first one, and the angle of incident of ray S is larger than critical angle of water. That is why total internal reflection occurs. Now, number 6, ultrasound is an example of a longitudinal wave. Define the term ultrasound. I would say that it is a sound wave which has frequency higher than normal healthy humans audible sound frequency, higher than, or you can say just higher than 20,000 hertz or 20 kilohertz. Now B, describe what is meant by longitudinal wave. So this is definition of a longitudinal wave. Wave means vibration of particle which is parallel to the direction of travel of wave or direction of propagation of the wave. C, ultrasound is used to locate objects below the surface of the sea. First part, describe how ultrasound is used to locate an object below the surface of the sea. You may draw a labeled diagram as part of your answer. I am definitely going to draw it. So this is the bird or a sheep. Okay, I'm not good in drawing, but still I'm going to draw it. This is water, right? This is an object. So I have ultrasound coming from the boat, right? Incoming or incident ultrasound. And then the object will reflect the ultrasound back to the boat and detected by the boat. Reflected ultrasound. Okay, this is a sheep, right? I would say that, okay, there's a device, we call it a sonar device. A sonar device on the ship, installed on the ship, sends out ultrasound into the sea. And what happened is that this ultrasound travels through the water, until, okay, the ultrasound encounter with an object. And this, what happened after that? This ultrasound being reflected by object and travel back to the sonar device, and the sonar device would detect, okay, sonar device detects the echo. What do I mean by echo? The reflection of the ultrasound to and fro, right? Echo and calculate the time. And calculate the time. So the distance of object is calculated by, okay, speed of ultrasound times the time taken to detect ultrasound, to travel to and fro, divided by 2. And we are done. And the second part, state one other use of the ultrasound. You know, ultrasound is being used in the medical devices. We call it as transducer, right? We need a transducer to direct the ultrasound into our body. But before that, you have to apply a coupling gel on the surface of your skin in order for the 99% of the ultrasound to be transmitted into your body. So ultrasound is being used to check internal body structure of a patient. Right, that's the answer. Now, number 7, a student sets up the circuit shown in Fig 7.1. A, determine the value of the current measured by the ammeter. So the current measured by the ammeter is the same current that flowing through the 6 ohm. Same amount of current flowing out from the 12-volt battery must be the same amount of current flowing back to the 6-volt battery. So it is 0.50 ampere. B, calculate the potential difference PD across the 6 ohm resistor. So since you have the current flows through the 6 ohm, you use Ohm's law. V equals IR. The current flows is 0.5 and the resistance is 6. Therefore, the potential difference is 3 volt. 3 volt is the answer. And you have to show part C that the PD across the 20 ohm resistor is 9 ohm. How do we show? 20 ohm and R are connected in parallel, so they share the same potential difference. The total potential difference, or the EMF, is equal to the potential difference across the 6 ohm and plus the potential difference between the 20 ohm or potential difference across R. So the EMF is given as 12, 6 ohm takes only 3 volt, and potential difference across the 20 ohm, right? So the potential difference across the 20 ohm would be 12 minus 3 ohm, 3 volt, 12 volt minus 3 volt. So V across the 20 ohm is equal to 9 volt. Done. And D, calculate the resistance of resistor R. I know that I need to find the current that flows through R. But before that, I need to find the current that flows through the 20 ohm first, right? So since I already know the potential difference across 20 ohm, for 20 ohm, yeah, V is equal to IR. That V is I2. So V across, the PD across the 20 ohm is 9. I need to find I2 times the resistance, which is 20. My I2 is equal to 0.45 ampere. You take 9 divided by 20. And after that, you know that the total current coming out from the battery, right, is equal to the current I1 and current I2. So I write down 0.5 ampere is equal to I1 plus I2. I got my I2 value. 0.5 ampere is equal to I1 plus 0.45. So I can find the current that flows through R, which is 0.5 minus 0.45, which is equal to 0.05 ampere. Now use back the Ohm's law. V equals to IR to find the resistance R. Right, V is 9 volt because 20 ohm and R are connected in parallel, so they share the same potential difference. I1 is 0.05 and you times the R. R is equal to 9 divided by 0.05 and I get 180 ohm. 180 ohm is the answer. Now, question number 8. State what is meant by electric field. Field is a region in which electric charge experiences, because electricity is about charge, experiences force, or you can write electric force. Now, Fig 8.1 shows the negative point charge. On Fig 8.1, draw only 4 field lines to show the pattern and the direction of the electric field due to the negative point charge. So you draw out here, same length, okay, same height, and then 1 mark will be given to the pattern and the second mark will be given to the arrows because electric field is a vector quantity. Arrow points into the negative charge because electric field flows into the negative charge. B, the potential difference or the PD of a lightning strike is 2.9 times 10 to the power of 8 volt. The energy transferred by the lightning strike is 4.5 times 10 to the power of 5 megajoules. Calculate the charge flow. In this case, I'm going to use E, electric energy, is equal to VIT, if you remember, and IT, Q it. This is a definition of charge. So I'm going to replace this. E is equal to VQ. Now make charge as the subject. Q is equal to energy over PD. Q is equal to energy is being given 4.5 times 10 to the power of 5. Remember, mega is one of the prefixes which carries the power of 6. 10 to the power of 6 divided by 2.9 times 10 to the power of 8. So in other words, I'm saying that it is 4.5 times 10 to the power 11 divided by 2.9 times 10 to the power of 8. The answer should be 1.55 times 10 to the power of 3. What is the unit of charge? Coulomb is the unit of charge. So 1.55 times 10 to the power of 3 Coulomb. Now see the current in lamp. In a lamp is 2 ampere. This lamp is switched on for a time of 120 seconds. Calculate the charge that flows. Calculate Q equals to IT. I is the current in ampere and time must be in second. It is given in seconds, so you just times 120. So your answer should be 240 Coulomb. Charge is measured in Coulomb. 240 Coulomb. Now, question number 9a, Fig 9.1 shows a transformer. First part, there is an alternating current in the primary coil. Describe how an alternating current is produced in the secondary coil. Now, you know that whenever there's a current, that is a magnetic field in the coil. So I will say that AC, alternating current, before that I explain first, alternating current. Okay, so I bracket, I put a symbol. So in future, I will use this symbol, right? This short form to represent alternating current. In primary coil, produces alternating or varying magnetic field. Right, in the primary coil as well. So the core, a soft iron core, soft iron core transfer alternating magnetic field to secondary coil. And what happened is that this alternating magnetic field is cut by secondary coil, which causes a change in the alternating magnetic field. A change in alternating magnetic field induces alternating current in the secondary coil. That's it. Now, the second part, a step-up transformer has a turn ratio of 1 to 20. The voltage across the primary coil is 12 volt. Calculate the voltage across the secondary coil. So you have to understand this is step-up transformer, meaning to say that the secondary voltage must be higher, first one, and the number of turns in the secondary coil must also be higher. So I'm going to use the secondary voltage divided by the primary voltage first is equal to the number of turns in the secondary coil divided by the number of turns in the primary coil. Remember, step-up transformer, step out. So the number of turns in the secondary coil must be larger than the number of turns in the primary coil. I'm going to write that down for you. This is number of turn in the primary coil. So Vs, voltage across the secondary coil, divided by 12 equals to, ratio is 20, so 20 has to give to number of turns in the secondary coil divided by 1. So V secondary coil is equal to 12 times 20. So the answer is 240 volt. 240 volt is the answer. B, the power loss in cable is 1.25 times 10 to the power negative 3 watt. The resistance of the cable is 0.05 ohm. Calculate the current in the cable. Since this is a power loss and the resistance is being given, I am going to use P equals to I square R. And I find the current. Current is equal to P over R, but you have to square root the whole thing. Now, power is given, which is 1.25 times 10 to the power of negative 3, and the resistance is 0.05. Now, use your calculator. You should be able to get 0.16 ampere. 0.16 ampere is the answer. C, state two advantages of high voltage transmission. So high voltage transmission, the main advantage is to reduce power loss in cables, transmission cables. And it also, since the power is being reduced, so it could also increase the efficiency of power transmission over a longer distances, because the power station is not built close to our household. That is why we need that to be as efficient as possible. Right. Question number 10. A, define a light year in word, right? 1 light year is actually the distance traveled by light in 1 year. That is called 1 light year. B, it takes light 490 seconds to travel from the sun to the earth. Calculate the distance from the sun to the earth. Now, I am definitely going to use speed is equal to distance over time. I want to calculate the distance. It is equal to speed times time. Speed is equal to 3 times 10 to the power of 8. That is the speed of light. Times the time, 490 seconds. So the distance is equal to 1.47 times 10 to the power of 11 meter. 1.47 times 10 to the power of 11 meter. That's the answer. See fix 10.1 is a scatter graph showing how the speed of the galaxies moving away from the Earth varies with the distances from the Earth. A scientist draws a best fit line on the scatter graph. Use this graph best fit line to determine the value for the Hubble constant. What is Hubble constant? Now, before I explain what is Hubble constant, you need to know the speed of the galaxy which is moving away from Earth is directly proportional to the distance, right? So I get rid of this proportionality is equal to the Hubble constant. Right? So to find the Hubble constant, it is the speed of the galaxy divided by the distance between the galaxy and the Earth. Right? It is actually you can actually find the gradient of the graph, or you can find the ratio. Why you can find the ratio? Because the graph starts from origin. Right, so I'm going to find the ratio. So the ratio that I'm going to use, the one that may be this one, right, which is close to the n. Okay, is it easier using this point here? Yeah, the point that on the here, this is my value. This is 112, and then the value here is go back. Okay, this is 8, right? 2.8. So I'm going to find the ratio. Okay, speed is 2.8 times 10 to the power of 4 kilometer per second. So I'm going to remain the kilometer because the distance is also in kilometer, divided by 112 times 10 to the power of 20. So 2.8 times 10 to the power of 4 divided by 112 times 10 to the power of 20, I get 2.5 times 10 to the power of negative 18, right, per second. So the answer is per second. So 2.5 times 10 to the power of negative 18 per second, or second to the power of negative 1. D, the speed of a receding galaxy can be estimated using a redshift. Describe what is meant by redshift. You know, galaxies, when they are moving away from us, they will give out light, right? Since the light, because the galaxies are moving away, the light given out is in the long wavelength. So the longest wavelength in the visible light is red light, right? So it will give out light in terms of longer wavelength. So what is meant by redshift? Redshift means the increase in the observed, because we see observed wavelength of the electromagnetic radiation emitted from receding galaxy and star. Okay, you can put galaxies because all the galaxies, right? Okay, and stars. So I'm going to put plural here, galaxies and the stars. Now, question number 11. Define the half-life of a radioactive source. Half-life is the time taken for a radioactive source to decrease to half of its original value or original activity or original count rate. B, a protactile Okay, a protactinium Pa nucleus decays into a uranium nucleus by emitting of a beta particle. Complete the nuclear equation for the decay. So you emit beta particle. So I write down beta particle first. Beta particle means fast moving electrons, right? Plus, and then you balance the nuclear number. This is 2, 3, 4. Balance the proton number, which is 91, is equal to 92 minus 1. This is uranium. And the second part, state the change that occurs in the nucleus during the decay. Could you see that? That this is 234, wait, 234 minus 91, you have 143 neutron, and 234 for uranium, you have 142 neutrons. So that means there's a decrease in neutron. What would happen? It is because the neutron changes to proton. That is why uranium has more proton, one more proton as compared to protactinium. Right, hard to pronounce the name. See, a different element decays by the emission of an alpha particle. Give two reasons why alpha particles are more strongly ionizing than beta particles. First reason is because, right, the alpha particle is, okay, the charge of the alpha particle compared to the charge of beta particles. The charge is larger. So I'll say larger charge. And second, it is because the alpha particle has a larger mass as compared to beta particles. So larger mass indicate that, okay, higher kinetic energy. So higher kinetic energy of the alpha particles as compared to beta particles. So that's the end of our discussion for this paper. So what I want to advise you is that keep practicing, stay consistent, and I will see you in my next video. And if you found that this video is helpful, don't forget to like and don't forget to subscribe so you will be the first one to get my next paper walkthroughs. Thank you very much for watching. I'll see you in my next video. Bye.